So I think we've heard a lot about interconnects today, what we have, and brief mentions around Ethernet. But I think it probably is good to just to remind ourselves of the position of Ethernet within HPC. Previous talkers, Steve and Professor Panda, talked about the top 500. And I think what's really interesting is as you look at that bottom line, is to draw out, as was identified by Steve yesterday, what the number 500 system is going to be in the range 2015. And so we're approaching petaflop capability in terms of even the number 500 position. And if you look at the occupancy of interconnects within the top 500, lo and behold, even last year, we're around about 42% of the top 500 is still Ethernet based. And there are a number of reasons why that exists. You can amortize the communication to compute ratio within the XHPL and achieve 50% performance on gigabit. And the other reason why it's used extensively in that is because it's free on the server. So the number of drivers that are going to happen over the next 2 to 3 years, some of which have been spurned on the collateral coming out from Intel last week around Sandy Bridge, which is driving 10 gigabit Ethernet on the motherboard. So what I'm actually going to do is talk about Gnodal with some blatant product marketing, but actually look at some of the levels of performance that can be achieved within Ethernet. Just to give you a background of the company, we were founded in 2007. The company has a track record in delivering large-scale network performance from its Quadrix heritage and its Mako heritage. It's good to see Mako mentioned again today in terms of Eric Barton. And we're using that capability to drive HPC network performance within the standard of Ethernet. As I say, we have a long track record of delivering high-performance networks. We've got a number of patents which are filed, which are underpinning the intellectual property of Gnodal. We launched in May last year and have had considerable success. In terms of socket-based communication within low latency financial services. In terms of HPC throughput, we're in the process of installing a very large cloud environment within the UK that's going to support some pretty demanding scientific computing and the storage required for that. And we also have some deployments within medium-sized HPC where even today 10 gigabit is good enough to deliver MPI performance on arrival to InfiniBand. In terms of the actual products that I'm going to go through, we've engaged with as we're quite a small company, we've engaged with a number of partners to be able to deliver these products worldwide. In fact, some of these financial services are being delivered in Chicago, New York, worldwide as we speak. Sorry. So Ethernet's on the move. So as I mentioned, 42% of the HPC top 500, as a suitable measure of HPC, is Ethernet. But Ethernet's been fairly constrained in terms of its deployments. It's been deployed in environments which tend to have north-south based communication, and there are a number of applications that are arising within commercial HPC. As well as scientific HPC, which are creating demands on Ethernet to move. It was created as a lossy, best efforts-based network. It's now moving into an environment in which there's going to be communication east-west in terms of reduction-based algorithms for business analytics, and these are driving Ethernet into the types of topologies that we're used to in high-performance computing, where we have a very flat device-to-device level interconnect, which should be sort of homogeneous across some very low latency. So Ethernet's on the move. There are a number of standards that are arising in terms of the ability to do lossless communication, also multipathing, as well as the requirement, the underlying requirement in order scalability and low latency. So there's a fundamental problem that's been hitherto experienced within Ethernet, in that you get, because of that north-south divide, you get congestion, you get reduced network bandwidth, you get high jitter on latency, and all these within particular vertical sectors can lead to lost trades in the cases of financial services, but poor quality of service. So what we've done at Gnodal is go back to first principles and actually looked at, well, the vision is to have HPC performance within the standard of Ethernet. And we've gone back to first principles and actually looked at the properties of the Ethernet frame, and is it viable to use that protocol as an ability to scale and support large latency? Well, the answer is yes, but it needs a little teasing. So going back to first principles, we've developed an ASIC. So while we're at Quadrix, and since then, we looked at using merchant-based silicon from some of our competitors' switches, and using that to see if we can scale out and deliver the types of performance within HPC that's required. Within the Ethernet model, there were certain constraints in terms of spanning tree. All roads lead to Rome, but you can only use one of them. So we've actually developed a new ASIC. It's fabbed for us by IBM. The property of that ASIC, it's an 18-way, 40 gigabit per second ASIC. And we can bring those high-speed SerDes out as one of those 40 gigabits as 410s, or we can support a 40 gigabit Ethernet MAC. And we can also support something what's called a Gnodal MAC. And this brings us back to the little teasing that's required in terms of the Ethernet frame in order to achieve high scalability, low latency, and congestion-free. The fundamental properties of the ASIC is it could support scales from a 72, so it's a 72 Arity, 72 10 gigabit, but can scale up to 64K ports. It's very low power. The PHYs are integrated on the chip, so we can provide switches which are very low power. And there are a number of patented congestion techniques that are operating in line in the data path of the ASIC, which allow us to provide congestion-free switching. Just a brief mention of the partners. So we're delivering these products worldwide with a contract manufacturer in Plexus, currently manufactured in Scotland, where Plexus has a footprint worldwide, so we could easily move production when the need arises. Where IBM are acting as our fab partner in a fairly modest 65 nanometer process. And then there was a back end from Arrow Electronics delivering PCBs to Plexus. And then we've licensed, of course, with Ethernet comes all the Cisco likeness and CLIs, etc. So we've, rather than reinventing the wheel, we've licensed the stack from Arison there in terms of delivering that protocol capability. So with the properties of the Gnodal ASIC, we can actually support Ethernet at the edge and then a Gnodal fabric behind that. The property of Ethernet at the edge is with our ASIC, we can support a 150 nanosecond ingress into the network, and then each switch hop in turn is 60. So I got 150 nanoseconds in, obviously assuming that there is some NIC that's within the server or the storage, and then each additional hop adds 64 nanoseconds. And so in this network, this scale of network was delivered to a DoD customer in the US. We could get across this network in 242 nanoseconds in an extremely flat fashion. And that's pretty good state of the art in terms of latency across the switch. So the key point is We've got Ethernet at the edge, and we do an encapsulation. So the teasing comes from doing an encapsulation or re-encapsulation of the Ethernet frame on ingress. So we support the Ethernet standard transparently at the edge, and then tease the Ethernet frame in this ability to support a nodal MAC between links within the network. Now these links are 40 gigabits a second. They auto-negotiate to when a nodal ASIC is connected together. They auto-negotiate to the nodal MAC. And the property of that nodal MAC allows us to implement a virtual circuit from ingress to egress. Yes, Brett? These are standard SFP plus or QSO. In this case, SFP plus. These are QSFP. And so we support passive, active, long reach cables as per the standard. Yes, so you do have to take into account the speed of light through them. So I was giving the non-cable based latency. So this is 64 nanoseconds through the switch, irrespective of the cable length. Up to jumbo frame, largest frame is 9K. As I mentioned, we're teasing the Ethernet frame. We support this nodal MAC that instantiates a virtual circuit back from egress to ingress, and down that virtual circuit comes feedback information about what's happening at egress. So at ingress, we very quickly, so this is why we require low latency, because you've got to operate at scale across the network. So you need this information back really quickly if you're going to affect packets at ingress because of behavior at egress. And that virtual circuit operates all the way through the switch hops of the network. So we can see what's happening at egress. We can see congestion. These are the current products. We have 3 products, better exemplified at the back here. As I mentioned, the Nodal ASIC is an 18-way, 40 gigabit per second switch. So we can bring those high-speed SerDes out as all 18-way. So we have an 18-way, 40 gigabit per second, 40 gigabit Ethernet switch here. We can bring them all out as 10 gigabit, supporting SFP plus. And then we can create hybrids in between. This hybrid here is 40 times 10 plus 840, which is the product that I showed previously in that fat tree that we're using to build. So we're taking 40 gigabit uplinks, which are instantiating the nodal fabric. These are very low power. This just gives some early sort of Visio diagrams but really saying that we're supporting standards here. So it's SFP plus or QSFP, and pretty low wattage per port. Switch management, excuse me. Switch management, as I mentioned, we licensed the Arison stack. We've extended that from its basic support to support a single pane management, so that from one switch I can affect the nature of a particular Ethernet port. I can set its MTU. I can set its VLAN from a single sign-in to a virtual switch. And then we have traditional management interfaces which allow integration within higher level management functions. Yes? No, it's a device level interconnect. It's a layer 2. Or there is some layer 2 plus features in terms of IJMP for multicast support and for flood and broadcast control, but it's a layer 2. It's effectively a layer 2 forward packet forwarded engine that we've developed. Under NDA, and we can talk to you about support for higher level protocols. Just to look at performance, as I mentioned, we've got on ingress, whether it's 10 or 40 gigabit, we've got a 150 nanosecond store and forward lookup. We're doing an encapsulation of the Ethernet. We're ejecting rogue frames. We're upscaling to 40 gigabits a second. So that has a cost of 150 nanoseconds. Here, for the benefit of Brent, I add a quarter of a meter of cable onto the latency through the switch. But we can see we can get into very large numbers of ports, around about 6.5K ports with half a microsecond across the network. Of course, we've got the nodal MAC operating across this. So when we see congestion, and to avoid, and to maintain a very low jitter, the worst thing you can do is just pile up and just continue to try and put packets through that network. So we can actually start to avoid congestion and reroute. We're not limited, but we have a multipath fabric in place, so we can use a number of routes through the network. And in the event of congestion, we can move a flow. And in that case, we actually have to take a hit in terms of the actual latency. But we're doing it for a good reason, because egress is slammed. So these are standard RFCs. These are the sort of things that the financial services industry, high frequency trading, they live and breathe. RDMA latency. We heard from Professor Panda earlier on in terms of the support of some of the RDMA capabilities that are available now in high-speed Ethernet. Some of those, Professor Panda was talking about Rocky and iWarp. So these are some measurements for just a simple send from one node to the other. So this is actually end-to-end in this case. This is taking not just the switch. This is actually the path. This is from user space to user space. And you can see we're operating, less than a microsecond node to node in this case. And obviously this is on a standard Ethernet frame. That will, so there are, there's payload as well as the additional bytes. Just some measurements for the network that I showed here. I'm looking at the difference. This is measured with a Unix clock, so the resolution is not that great. So this is the average latency difference from one node to another node across this network. So I'm measuring around about 150 nanoseconds. Well, theoretically, that should have said I was 128 nanoseconds. As I said, there's some resolution on the clock here. So we're actually beginning to be able to measure this. There are a number of protocol engines, like the IXU devices at Spirent, that are used in financial services, which can give a higher accuracy in terms of the hop latency. Unlike our network, which delivers packets in order always, this presentation isn't. So I'm just going to skip those two slides and come back to them. So very low latency is required in order to provide scalability. The information coming back across this virtual circuit needs to be done very quickly. There are a number of other techniques in play within the network. This is just another example, which is what we call distributed fairness. And so I have a test engine here, which is the most simplest. I can construct a TCP transmitter and a TCP receiver here, and I have two switches with two nodal fabric links between them. And then I'm going to cause congestion by having a number of UDP streams, which are going to be very aggressive. They don't need to require for an acknowledgement to come back. So they're going to consume. I can wind them up to full line rate. And what we see is one of the other techniques in play within the nodal network, which is this idea of fairness. So as part of the encapsulation process, we tag each packet with its life in the network. And we can use that then to prioritize packets through the network based on their age. So in the case, I can actually take a degenerative step here and force it to be in 40 gigabit Ethernet mode as opposed to nodal fabric mode. And what we see here, we're starting from 10 gigabits a second because spanning tree and header-line blocking. I begin to lose performance immediately here. And this is because the UDP streams are on that right-hand port of the switch are taking the lion's share of bandwidth. In here, to the point of oversubscription, the point of incast, as you will, I can maintain full line rate between those switches, and then when I reach incast, I see it drop off, but drop off to half the bandwidth. So I'm giving TCP and UDP a fair share of the available network bandwidth. If I had a second link, I continue providing full line rate between TCP and TCP transmitter and receiver. Quite a busy graph. This takes it to the extreme of 3 switches. In fact, this customer had measured on a single switch the abilities of the fairness and wanted to see this maintained across the fabric. And so what we hear, in this case, we need to add UDP congestors at every point in the network, and then we measure the available bandwidth at each point in that network. So how much of the bandwidth is available to this TCP stream, which is the one of interest, not to these random congestors within this network. It's quite a busy slide. It takes some understanding, but what we see at the result here is, again, a third in terms of the available bandwidth for that. So it's providing the fairness. These purple ones do not get an unfair level of performance as opposed to this TCP stream operating across the network. So putting this all together, we can look at a sort of, I mentioned those in the past, 42% of those systems in the top 500 are using gigabit, but they're not there to just be they're not there for a capability machine. They're going to support a workload. And as we move forward, systems are not just dedicated to one capability system. I'll come to the sort of exascale type capabilities in a moment, but really these systems are going to operate in a general workload. So the next set of slides to show you sort of an example of a traffic class pattern which we may expect in a system. Okay, so I'll just skip on. There are a number of, I'll skip to the next slide just to show. This is what we would expect with typical Ethernet switching, 512 nodes implemented in a factory. Header line blocking, spanning tree will constrain the performance to these congestion endpoints here. Proprietary switching will do some of the techniques we pioneered at Quadrix, would give you some benefit in terms of aggressive random routing. The techniques, low latency, fairness, would lead us to this, which is almost the holy grail. Built from distributed switches, I have an arbitrary large switch. This is a slightly deprecated one where there's no topology. It's actually a rat's nest. So there isn't just a magic bullet, one silver bullet that can get you to this. There are a number of techniques that build up on each other to move it forward. Just in a blatant bit of advertising, this is the sort of European equivalent of Project Moonshot, where we're going for Mont Blanc, not the moon. So this is the sort of part of my work package 2 in the dissemination of the Mont Blanc project is to just call to your attention. There's a great article in Scientific Computing World written about this from mobile phone to supercomputer. And this looks at using commodity components to pave the way towards exascale using, in this case, low-powered processors from